this screencast, we're going to be going over the answers to the solutions and net ionic equations homework. So question number 1 was just a bunch of net ionic equations, just so we had practice. Hopefully you sat down with your reactions to know page and tried to follow all of those rules. A lot of the reactions are double replacement, but we have learned a few synthesis reactions, and we'll be learning some more decomposition and, of course, single replacement. 1A is a acid-base reaction, and one of your products is always going to be water. Water is a molecule, so don't try and split it into ions. Kf, which is formed, is soluble. Anything bonded to something in group 1 always is. We don't show HF as ions because it is a weak acid, and so it is splitting up and getting back together, so we can't represent something as ions when it actually isn't. And KOH is soluble because, again, you have something in group 1, then canceling out your spectator ions, you end up with this net ionic equation. 1B, we have magnesium sulfide and some nitric acid. You have to make a decision about your nitric acid. It is a strong acid, so it will split into its ions. This is a double replacement reaction. Magnesium nitrate, all nitrates are always soluble, so this does split up into its ions. HS does not split up because it is a gas, and it's one of those gas-forming reactions that you have to recognize. We did not split up magnesium sulfide because in the problem it says it's a solid, so it will react, but at the beginning, because this is what we're showing, the reactants, what's there at the beginning of the reaction and what's there at the end of the reaction, we cannot show magnesium sulfide as ions because it's a solid right now. It will dissolve in the nitric acid and will react, but at the beginning it is a solid. C, we have acetic acid poured into sodium bicarbonate. So these are this is the acid-base reaction that you would do, or at least, anyway, the reaction that you would do in a volcano, like in the 3rd grade. So you have your acetic acid. It is a weak acid, so of course you don't split that up. Sodium bicarbonate or sodium hydrogen carbonate is another name for that. It is a solid because in the problem it says powdered, so we're not going to split that up. It's going to form sodium acetate. All acetates are soluble, especially if it's bonded to something in group 1, so we have our ions there. And it does form carbonic acid, which immediately breaks down into water and carbon dioxide. Again, these are your gas-forming reactions that you just need to know and be able to recognize immediately. In 1D, we have ammonium hydrogen sulfite and perchloric acid. So, and both of these are solutions. This will split up. Most things bonded to ammonium are soluble. And perchloric acid is a strong acid, so it also splits up into its ions. We form ammonium perchlorate, and we form sulfurous acid, which breaks down immediately into water and SO2. Again, a gas-forming reaction you have to be able to recognize. E is one of our reactions to know. We've got solid lithium and it's added to water. These guys are part of the alkali metals, and that's because they form basic solutions when mixed with water. We are going to form a base and hydrogen gas. Water is a molecule, so again, we do not split that up, and lithium is solid. Notice there is no charge because lithium is a metal and it is metallically bonded to other lithium atoms, resulting in no charge. Over here, though, when lithium becomes an ion and bonds to hydroxide, you do have to show it as a ion charge, and this does split up because it's group 1. Similar situation here, we've got potassium oxide added to water. Reactions with water are some that we are trying to memorize, so it's in our reactions to know part. And we have our potassium oxide added to water. This is going to result in just a base, no hydrogen gas like the previous problem. Granular potassium oxide means it is a solid. Water is a molecule, so we don't split either of those up or represent them as ions in our net ionic equation. Potassium hydroxide is soluble, so we are going to split that into its ions, making sure you balance as you go. Here we have a nonmetal oxide added to water, and it is going to form an acid. And the acid here is sulfuric acid. That is a strong acid, so it does split up into its ions. We don't split up our two molecules. In H, it's solid magnesium oxide and exposed to carbon dioxide, and that is going to form magnesium carbonate. Besides the fact that most carbonates are insoluble, the other reason we don't have this shown as ions is because there is no water involved here, so we're not dissolving anything. Magnesium carbonate would just form and would be in the solid form, resulting in no ionic charges. I is a single replacement reaction. It's one that you have seen. Copper put into silver nitrate. Of course, nitrates are all soluble, so they do split up, and that's one of the few compounds that will combine with silver and not form a precipitate. Copper comes in and replaces the silver, so we start to see silver precipitate, and we're going to form copper nitrate solution, which, if you remember, solutions that involve copper are blue. And they could ask you about some of those practical aspects on the AP exam about those chemical reactions. So the resulting net ionic equation looks like this. Remember, a solid piece of copper is metallically bonded to other atoms of copper, and so there is no charge here and cannot be canceled out with copper here, which is an ion form because it is separated from the nitrate by water. Similar situation goes on here with the silver ions versus the precipitated silver crystals that would be forming as a product. Make sure that you do balance for charge, and that's really what's going on here with these coefficients. And then the last one, at least as far as our net ionic equations go, we've got solutions of hydroxide and nitrate. Both of those are soluble. It is going to form strontium nitrate, which is soluble because all nitrates are, and iron 3 hydroxide, which is a precipitate. Most hydroxides are insoluble. So when you get rid of your spectator ions, this is what you end with. But when you write net ionic equations, you want your coefficients to be the lowest possible whole number ratio. So just reduce that down to get your final answer here. Okay, question 2 on the homework, and ask about the intermolecular forces. So intermolecular forces affecting atoms from weakest to strongest. So we would have started with London dispersion forces, and that's also called an instantaneous dipole, because when we say that the electrons are being shared equally, it's not equal all the time. And because it's not equal all the time, when other nonpolar molecules get around more nonpolar molecules, that there is an instantaneous attraction there, but it doesn't last very long and it's not very strong. It does increase with size of the molecules because you end up with more electrons and they become a little more polarizable. Then you would have dipole-dipole intermolecular force, forces of attraction. Those occur between polar molecules, and it's that partial positive attracted to that partial negative. It is stronger than London dispersion forces, and also becomes stronger the more polar the bonds are, which would result in a more polarizable atom or molecule. So then we have an extreme form of dipole-dipole, and that is hydrogen bonding. It exclusively involves hydrogen, and it has to be a hydrogen directly bonded to F, O, or N. That makes that hydrogen very electron deficient, makes it hungry for more electrons, and that allows it to become attracted to an unshared pair on a neighboring molecule. And that unshared pair is generally on fluorine, oxygen, or nitrogen as well. Okay, so in order to lead us through this, we're number 3, I had you go through the substances. Since we're still practicing our Lewis structures and bonding, I made you go through this progression here so that you could figure out what type. Okay, Here we have question number 3. So you needed to look at the substance, draw the Lewis structure. You needed to evaluate whether the bonds were polar or nonpolar. And you would have done this by finding the electronegativity difference. You could find the values in the book. Then I wanted you to determine, based on whether it had polar or nonpolar bonds and the Lewis structure, whether the molecule is polar or nonpolar. And from that, you should be able to make your decision on which has the strongest intermolecular force, or what is the strongest intermolecular force present between the same molecules. So the first one, you end up with CS2. This ends up having a structure that looks like this. You find that there is very little electronegativity difference, actually no electronegativity difference between carbon and sulfur, making each of these bonds nonpolar. Because the bonds are nonpolar, there is no way you could have a polar molecule. So the molecule itself is also nonpolar. This is pretty rare for two different elements to have the same electronegativity unless they are the same element. So the strongest London or the strongest intermolecular force present is our London dispersion forces. Then we have carbon tetrachloride. It ends up with this nice tetrahedral structure. The carbon chloride bonds are polar. You end up with an electronegativity difference of 0.5, but because the molecule is symmetrical, the molecule as a whole is nonpolar, meaning that, or because the dipole nature cancels out. So again, all we have are London dispersion forces between molecules of carbon tetrachloride. With ammonia, the structure looks like this. We have 4 things around a center atom, 1 unshared pair, so this is trigonal pyramidal. And the nitrogen-hydrogen bond is quite polar. We end up with a 0.9 as the electronegativity difference between those two atoms. And the molecule itself is polar because it is not symmetrical, so the dipoles do not cancel out. This molecule ends up having hydrogen bonding between ammonia molecules because you have a nitrogen bonded directly to a hydrogen. So this hydrogen here is electron deficient and will seek out other unshared pairs. Methane, we have CH4. It ends up again with a nice tetrahedral arrangement of the atoms. These bonds are very slightly polar, and that's important for you to remember. The CH bond only has an electronegativity difference of 0.4, so even though it's polar, it's just barely polar. And that will come into play when we look at larger molecules, and most of those involve the carbon-hydrogen bond. But because of the tetrahedral arrangement of these atoms, we end up with a non-polar molecule. It is symmetrical, so the dipoles cancel out. And so we only have London dispersion forces between molecules of methane. SO2, its structure, it ends up having to be a resonance structure, so you would have had to draw on both. This is bent, so we've got 3 things around a central atom, but there is 1 unshared pair. And the bonds, the SO bonds, are polar, quite polar. They have a electronegativity difference of 1. And the molecule itself is polar because of this unshared pair on the center atom. It makes the molecule non-symmetrical. So we have a polar molecule, and this would undergo dipole-dipole interactions between molecules of SO2. Water's structure we should be very familiar with, this bent structure with 2 unshared pairs on oxygen. The oxygen-hydrogen bond, again, is very polar. We've got 1.4 electronegativity difference. And the molecule itself is polar because that bent structure is not symmetrical, so the dipoles can't cancel out. We have a hydrogen directly bonded to an oxygen, and so this hydrogen is very electron deficient, so we will have hydrogen bonding between water molecules. PCl3 ends up having a nice trigonal pyramidal structure with an unshared pair on that center atom. The bonds between phosphorus and chlorine are all polar, and you have a polar molecule because it is a non-symmetrical molecule, so the dipoles cannot cancel out. So we would have dipole-dipole interactions. HF The bond here is a very polar bond. This bleeds over into what we classify as ionic bonds. The attraction, fluorine has a very high electronegativity. This is still classified as a molecule, so we will call it a very polar molecule instead of ionic. Although when we do write the formulas for acids, we do use the charges in writing those. We have polar bonds, and of course it is going to end up being a polar molecule. It only has two things in there, and this is hydrogen bonding. So this hydrogen is very electron deficient and will seek out other unshared pairs. Chlorine gas, we've got two chlorines bonded to each other, so it is a nonpolar bond with an electronegativity difference of 0. So it forms a nonpolar molecule and only has London dispersion forces. SCO ends up looking like this, very similar to the structure we had at the very beginning of this problem. The sulfur-carbon bond is nonpolar and has no electronegativity difference between those atoms, but the CO bond is polar, and quite a bit so. That means that oxygen's going to be pulling on the electrons not only from carbon but also from sulfur, resulting in a polar molecule overall. This would have dipole-dipole interactions. Then the next two problems were just some basic concentration problems. So the first one is a dilution, where we're going to use MCVC equals MdVd. And in most of these problems, at least the realistic ones, you're going to be solving for VC. We want to figure out how much of this concentrated solution we need to prepare of this molarity. So you work the problem this way, and it would be 16.7 milliliters. Be careful with the way the question is worded. I could have asked, how would you prepare this solution? And 16.7 milliliters would not answer that question. You would say that you would need to take 16.7 milliliters and add it to some water that was in a 100 milliliter volumetric flask, and then you would add some more water till the bottom of the meniscus was at that line. That would form your 2 molar solution. Of course, you would want to have water in that volumetric flask before you added the acid, because you always add acid to reduce the chance of having a lab accident. Number 5 is a basic molarity problem, but it does involve a hydrate. So we have copper 2 sulfate pentahydrate. You have to get the molar mass of that. So you're going to find the mass of the copper 2 sulfate and add the mass of 5 waters, resulting in this molar mass. We have molarity and liters. And so you would multiply those together to get your moles, and then use molar mass to convert to grams. If we had 3 sig figs in here, it would be 0.250 grams. I think the way it's actually written, it would end up just being 0.2 grams.